Hello, and welcome to day 11 of Advent of Code. Today we have a problem called cosmic expansion. And before we get into this, I just want to say that I am sorry if the keyboard or mouse, I guess trackpad in this case, is extra loud today. I am using my laptop, so hopefully it is bearable, but I'll do my best to type quietly. So in this problem, we have a grid or a graph of galaxies, and the galaxies are denoted by hashtag or pound signs, and then there's also empty space, which is denoted by the dots. And the idea is we want to sum across the shortest path between every pair of galaxies. And we can only move in the cardinal directions. So the shortest path is then, by definition, the Manhattan distance. So essentially, we want to sum the Manhattan distances between every possible pair of galaxies without duplicates. But the caveat is that if there's a column with empty, that's entirely empty, in other words, it contains no galaxies, or there's a row that is entirely empty, in other words, it also would contain no galaxies, then we need to duplicate it. So basically the idea is that like the universe is expanding, or that's what they're telling us in this problem. So all of the empty rows and columns are duplicated. And so we could brute force this. And what I mean is we could actually duplicate the size, or not the size, but duplicate these rows and columns. And that would work for the first problem. But it turns out that in part 2, rather than duplicating it, we're actually multiplying those, or we're doing it not just twice, but a million times. And obviously that grid will become far too large. So we want to be a little bit more clever about what we do in part 1 to make part 2 slightly easier. And so what we're going to do is basically, we're just going to go about calculating the distance as we would if the grid did not expand. But what we're going to do is every time we encounter a galaxy and want to check it against another galaxy, we're going to check if the galaxy that we're currently looking at is, if any of the rows that are between it and the galaxy against which we're comparing it, and same thing for columns, are contained within the set of empty rows or empty columns, right? And so this will make a little more sense when we start coding it. But then if we do detect that to be the case, we can just add 2 instead of 1. I think it will be easier if we just get into the program here. So I'll open up a new day. I'll run my script to get the input and create a folder, and then I'll cd into that folder. And I'll open up part 1. And let me X out of the terminal for now, and I'll even go a little bit larger here. So, all right, beginning with a solution. So our graph or grid, or whatever you want to call it, is already in the format we want it, or at least for me it is, because it's already a vector of strings. And so I'm just going to set graph equal to input. Great. And then now I want to initialize 2 more vectors, this time of integers, called empty rows and empty columns. Okay, and then finally I want to have a place to store the galaxies, and so this is going to be a vector of pairs of integers, where each pair corresponds to a coordinate on the grid or graph. And then what we're going to do is we're going to figure out which rows are empty. So for int r is equal to 0, r not 9, 0, r is less than graph.size, r++. We're going to set a Boolean value called row is empty equal to true, because it will start off assuming that it's empty. And then if we run into a galaxy, then we will be able to set that Boolean equal to false. So we'll say if graph at r at c is not equal to empty space, then we know that the row is empty is false. And we also want to check, so actually you could just do this all with one if statement because there are only 2 types of characters. But when I was writing this, I didn't know if in part 2 they maybe would introduce another type of character or something like that. So I just do it in 2 separate if statements where I explicitly check whether the character we're looking at is in fact a pound sign. And then also if the row is empty, so if row is empty, we want to empty rows dot push back r. And then we can just copy this and do the same thing for columns. The iteration will be slightly different though, because we want to start by iterating through the columns. So C will go here, and then we'll set this equal to call is empty. And then rather than using C here, we'll use R, and this will just be graph.size. Let's see, what is it upset about? Expression must have a comma. Oh, this needs to be a C. Okay, and then we can get rid of this and make this C and make this empty columns. Great, and that should be everything we need to get our list of empty or vector of empty rows and of empty columns, as well as the galaxies. And then I'm going to define an integer value called scale factor, which for part 1 will be equal to 2, because this is how many times we duplicate a line if it is empty. And we'll iterate through the galaxies. So for int I is equal to 0, I is less than galaxies, dot size, I plus plus. We want to say that our current pair, or actually it's just, we'll call it galaxy, is equal to the galaxy at index I. And we'll say int R1, so remember we're going to compare galaxies against each other to find their Manhattan distance, is equal to galaxy.first, and int C1 is equal to galaxy.second. And then, so now we're going to iterate through all of the galaxies up to our current galaxy, because this will allow us to, first of all, check every galaxy against every other galaxy, but also avoid duplicating that check. So that's why we use j is less than I here rather than j is less than galaxies.size. Technically, you could set up a way to do it with iterating, kind of a double for loop through the entire galaxies array, but then you'd have to remove duplicates after. So this just does it kind of all in one sweep, which is handy. And then this will be, the other galaxy will be equal to the galaxy at index j, and then we'll say int R2 is equal to other galaxy dot first. And then I'll just copy this, and we can say second, and this will be C2. And then what we want to do is we want to basically calculate the Manhattan distance. And the way we're going to do that is by iterating through. So normally what you could do is you could say like answer is equal or plus equals like R2 minus R1, right? Like that's the formula for a Manhattan distance. And it also then would be, you'd have to do it for the column because you can't move diagonally. But rather than doing it this way, we need to actually iterate over the range between R1 and R2 and dynamically choose whether or not we're going to add 2 or just 1 based on whether or not the current row is in the empty rows vector. So to make that a little more concrete, we'll say for int r is equal to, so it's going to start at the min of R1 and R2, and it's going to go to the max of those two values, R1 and R2, and of course we'll increment it by 1. We want to check whether empty rows contains R, right? So we want to check if we're looking at an empty row right now. And the way we'll do that is just with this syntax, using the find method, empty rows.end. And then we're going to say ants. So if it is contained within the empty rows, then we need to add the scale factor, which is 2, because that means we've duplicated that row. Otherwise, we can just say ants plus equals 1. And then we need to do the exact same thing for the columns because we are using the Manhattan distance, not the diagonal shortest path. So I'm just going to change all instances where I say R to C. And then we want to do empty columns. And that should be all we need to do. And then I believe we'll have our answer. So let me go ahead and compile this, crun part1.cpp. And one thing I did forget to do was actually grab the test input. So let's go ahead and grab this grid, and we'll paste it into our test.txt file, or however you're storing your test data. And then we'll do part 1 on the test input. And we do get 374, which that should be our answer. And then for our real input, for my real input, let's see what we end up getting. We want something 90 or 9, yeah, 9,639,160. That looks correct. Great. All right, and now for part two, I didn't really give us a chance to read through it. The galaxies are much older and thus much farther apart. So now we need to make each empty row or column 1,000,000 times larger. And luckily for us, we actually built a very scalable solution in part one. So I'm just going to go ahead and copy all of my code from part one and put it into part two, and then just change this output line. And all we have to do, so we actually need to make a few modifications. The first is just to change the scale factor from 2 to 1,000,000. But then, of course, because we're working with such large numbers, we want to get out of working with integers. So we're going to make this a long, long value, and we're also going to make our answer a long, long value. And then we can go ahead and compile part two, run it on the test input. And I don't believe it actually gives us an answer for the test input. I think it just shows you, like, yeah, it says what would be the case if you made it 10 or 100 times larger. So let's go ahead and use the real input to validate our solution. And we get this massive number, so I'm going to go ahead and copy this and make sure it is correct. And that looks great. All right, well, a bit of a shorter day today, but I hope everything made sense. Let me know if you have any questions by leaving a comment. Thank you so much.